You've seen it a million times in sci-fi, right? In shows like The Expanse or movies like Interstellar, people are just walking around on spaceships. Artificial gravity is a given. But how would we actually build it? Well, it's time to separate the hard physics from the sci-fi fantasy.
The second you enter orbit, this is what happens. It's not that there's no gravity. It's that you're in a constant state of falling. You're just moving so incredibly fast sideways that you keep missing the Earth. You are weightless. And yeah, that initial gut-wrenching nausea might eventually fade, but believe me, the real problems are just getting started.
The thing is, our bodies evolved over billions of years with the constant pull of Earth's gravity. Take that away, we are just not built for it. The long-term effects of floating around are, frankly, pretty severe.
Without gravity constantly pulling on you, your body basically starts to break down. Your muscles wither away, your bones lose density at an absolutely terrifying rate, about 1% every single month. And all that calcium that leaches out of your bones, it can start to build up in your soft tissues, which is really dangerous. This is why astronauts on the ISS have to work out for over 2 hours every single day, just to slow down the decay. If we ever want to live in space for years, let alone generations, we're going to need a better solution.
So, okay, how do we fake it? How do we create gravity where there is none? Well, physics really only gives us two options, and as you're about to see, only one of them is even remotely plausible for a long-term home out in the black. So option one, we could just build a spaceship that's constantly accelerating at 1g. Einstein's equivalence principle tells us that this would feel exactly like real gravity. The problem? The amount of fuel you'd need is, well, it's just astronomical. It's not going to happen. That leaves us with option two, rotation. You spin the habitat, and the centrifugal force, which, yes, is a fictional force, pins you to the outer wall. It's the only other way physics allows, and it's our best bet. Now, this idea of a giant spinning habitat isn't some newfangled concept. Way back in the 1970s, a couple of foundational designs came out that have pretty much defined how we think about this stuff ever since.
And the scale of these things is just, it's hard to even wrap your head around. We're talking about the O'Neill cylinder, a spinning tube 20 miles long with a surface area about the size of New York City's 5 boroughs. Then you have the Stanford Torus, which is shaped like a giant donut. It's much smaller, but in return, it's a whole lot less massive and potentially more stable.
Look at that number. That's $100 quadrillion. That's the estimated price tag to launch the materials for an O'Neill cylinder from Earth. To put that in perspective, that's about 1,000 times the entire world's GDP right now. So yeah, that makes one thing crystal clear. You don't launch these things, you have to build them in space using materials you mine from the moon or from asteroids.
But let's just pretend for a second we could build one. There's this other problem, a hidden, really counterintuitive quirk of physics that comes from living inside a giant spinning can. And this is where things get really weird.
It's called the Coriolis effect. Now, it's not a real force pulling on you, not like gravity. It's an effect of inertia. Your body always wants to move in a straight line, but the floor underneath you is constantly rotating out from under your feet. This creates the feeling, the sensation of a mysterious force that's always trying to push you sideways.
Let me try to make this simple. Imagine you're standing on the inside of one of these spinning cylinders. Someone outside, looking through a window, fires a cannonball from one side to the other. To them, the cannonball flies in a perfectly straight line. But to you, standing on that spinning floor, it looks like the cannonball follows this really bizarre curved path. That curve, that's the Coriolis effect making itself seen. So what would this actually feel like? Well, if you walk in the same direction as the spin, you'd feel a little heavier. Walk against it, you'd feel a little lighter. Okay, that's maybe not so bad. But the real problem comes when you try to move up or down, say climbing a ladder towards the center hub. The Coriolis effect would create this constant tipping force, pushing you sideways. It would feel like the floor itself is tilting beneath your feet. And that constant tipping and twisting feeling, that's not just disorienting. It leads to a massive engineering problem. Our inner ear, our sense of balance, and our tolerance for nausea, or lack thereof, create hard physical limits on how you can design one of these worlds. So here's the fundamental trade-off. To get that comfortable, Earth-like 1G of gravity, a habitat with a small radius has to spin really, really fast. But if you build a much larger habitat, it can spin much more slowly to get the exact same effect. And that spin rate? That turns out to be everything.
Because it turns out, through a bunch of experiments, we've learned that humans really can't handle spinning faster than about 1 or 2 revolutions per minute. Any faster, and we get something called canal sickness. It's a deep, persistent, and just awful nausea and disorientation. And this one single biological fact is why designs like the Stanford Torus have to be nearly a kilometer wide. They have to be enormous, just so they can spin slowly enough for us to live inside without constantly feeling sick. But there is a catch. All those tests were done here on Earth, inside giant rotating rooms where you still have Earth's gravity pulling you down. So the combination of forces people felt in those experiments is actually different and maybe even worse than what you'd really feel in space. So it's possible, just possible, that this 2 RPM limit is a little too pessimistic.
And as if making everybody sick wasn't a big enough hurdle, there is another problem. One that's actually far more dangerous and threatens the stability of the entire habitat.
It's a fundamental rule of physics that any object is only stable when it's spinning along its longest axis or its shortest axis. If you try to spin it along its middle or intermediate axis, it becomes unstable and starts to wobble. You might have seen this in that famous video from the ISS, where an astronaut spins a T-handle and it just unpredictably flips over and over in midair. That's not a fluke, that's physics.
Now, for a long, skinny habitat like an O'Neill cylinder, this is a catastrophic risk. It's designed to spin stably along its long axis, sure. But what if a big chunk of mass shifts, like a train moving along a track? Or worse, an asteroid hits it. It could get knocked into an unstable rotation and start tumbling violently. The Stanford Torus, on the other hand, spinning like a flywheel on its shortest, most stable axis, wouldn't have this problem at all.
So when you put all of this together, the insane cost, the weirdness of the Coriolis effect, the risk of the whole thing just tumbling out of control, where does that leave us today? Honestly, this timeline says it all. These incredible, grand concepts were dreamed up almost 50 years ago. A much smaller, more practical demo for the ISS was proposed, and then it got canceled. As of today, there are no concrete plans for any dedicated artificial gravity experiment in space. These brilliant ideas are still just that, ideas on a drawing board.
Which really brings us to the final and most important question. We know it's biologically necessary for us to live long-term in space, but we also know the challenges are immense. So should cracking the artificial gravity problem be a top priority for us? Or are we just destined to remain stuck to the planets we were born on?